okei, aga siis ma inglise keeles. Okay. So, good afternoon. So, first of all, thank you for all our speakers in the morning session. Of course, they were very perfect speeches, but I can say I unfortunately have not so perfect preparation because I will talk about an ongoing study, and so it's quite theoretically. It takes time to formalize it all as much as perfectly as possible, and so I will more or less offer you some more or less demonstration lesson and show what I have done. This I want to talk about pitch class sets in microtonal context. So, as we know, too much material goes. So pitch table. I think I have it here on this. So, table of pitch class sets is something what systematize every combination in in the traditional pitch class system. Of course, it was established by Alan Ford in the 70s, and it is something like I will see it as a combinatorial research. What combinations, if we have 2 pages, 3 pages, or up to all the pages, and what combinations there will are, and what are certain types of symmetries and features. So of course, and that is on the one hand this pitch class set, and I try to very briefly to describe all these theoretical things. Because I think some of you maybe will listen topics like that at the first time. For others is more familiar. We have to manage that. And this is one theoretical thing. The other theoretical thing is that microtonal systems I have talked yesterday. And of course there came up the question why there is certain systems are preferred before others, and why, for instance, 19 dividing the octave into 19 equal pitches is more preferred than others. And I found, of course, I have a little bit prepared how to reason it, and of course it is even, there is even a little sort of history behind that, what I only a little bit strive with, because generally the idea to have more than 12 pitches or have different pitch versions of chromatic keys is quite old, and it comes directly from these problems of tuning. Of course, generally, I have to introduce the concept what is named what is named the, I think I have it written here, the MOS scales. So there is as we know all from, is it working? Okay, then I go to the physical one. So, as we all know from elementary music theory, we have the circle of fifths, like, and so we have 12 times and we come around. But of course, it's really good working on this 12 to equal temperament. But in other tuning systems, it doesn't work like this. But now it's interesting how, if we look on which fifth we come nearly to the octave. And let us count. So we have here C, G, okay, we have the D, but okay. So we have, so we come here around the E. So we have something like the pentatonic or in this region. And of course, if we have the, it's a little bit simplified what I described, and of course, if we have 7 fifths, then we then here, of course, this pitch is nearly to the octave, and if we circle further, then we get 12 fifths. Of course, this is the so-called Pythagorean comma, what is quite well known, and it's a little bit higher we come out than the octave it must. And of course, but generally it is not necessary that we end by 12 fifths. If we continue that, then we will consider that we have 19 fifths, and then we come near to the octave, and then we count again the fifths upper and upper and upper, and then we come by 31 fifths. So there are certain numbers what fulfill the octave if we bring it back to the octave, and of course that is that what Wilson has described as the so-called moment of symmetry, and he made a whole theory of that, but generally if you have one interval what we count up and up again, what is also called in this theory the generator, and we have another interval what is the framework within we have to project it. This is the period, and of course the interesting thing is that of course things like these 19 pitches in octave, or even 31 pitches in an octave, these concepts were also approached in maybe in a little bit different way as today, but this was approached also 100 years ago, as we know this. Maybe everybody has in history heard about the Nicola Vicentino's archicembalo. So, and it was 1555, and there we can see that the lower manual has exactly 19 pitches in the octave. Of course, the upper manual has it's together 36, but it's based on of course this circle of 31 pitches, and later Christian Huygens was of course talking about the what he names harmonic cycle, where what he mentioned that if we have in a mean to mean tone temperament, in a quarter comma mean tone temperament, they have here shown the values. If we go around 31 times, then we have really the error is very small. So, and that was for proposing 31 pitches in the octave. Okay, shortly about mean tone temperament, what was in the Middle Ages before equal temperament was winning the fight. So there was the idea you have just in tone the major third. So, and then after the major third, you adjust the fifth. So the fifth is not so good established as in 12 tone equal temperament, and so this leads to this 31 tone scale. But if we have another mean tone temperament, what is this one third comma, or 1/3 of the so-called syntonic comma, and this takes the minor third, and if you take the minor thirds as pure as 6/5, and then from that you derive how large must the fifth be that the minor third is pure. Okay, you have the calculation here. I don't have no time to talk about all that. And then we get the circle of fifths looks like this, and And here we have 5 times, 7 times, 12 times, 19 times. And 19 times is here the most ideal one. It's just 1.2 cents. And of course, if we have this 19 times the 1/3 comma mean to 1/5, of course, is not already an equal division of into 19. But you see the error is very small. Then of course also the errors in the fifths are very apart from that. And of course, if I found that there was even one composition in that time, so there was also practical experiments. Maybe I find it. If not, then we skip it. No, then okay. Let it be. I think I switch it off. Okay, but that will show this, of course, microtonal tuning and this theory. It exists as a really little niche, but due to technical and practical problems, there are no practical results. But nowadays we have computers and sound systems, and so I think we have better conditions than 100, 200 or 300 or 400 years ago. So, okay, let's go back to pitch class set theory. Of course, pitch class set theory is something like an extension of chord theory. Of course, if you have for instance, the most well-known major chord, and normally we take in our pitch system that we can rotate the pitches, and we just classify at one and the same phenomenon. So, and okay, we do it also with maybe the dominant 7 chord. Of course, we can even do it like this. If I transpose that down, then we have. But even we classify it as one and the same phenomenon. And but of course there is a number of chords we name due to analysis of traditional of classical music. But in contemporary music and atonal music, in theory, every combination of pitches can appear as a chord or as a scale or as a little melody or whatever. But for that there is a problem to name that. And for instance, we use a cluster like this. And but of course we can even make these rotations. Like this. I think it was not correct played, but you get. I hope you got the idea. And for to formalize that, we have problems. To calculate, of course, with traditional node names. For to formalize that, was established by Alan for the so-called pitch class set theory here, and here I a little bit try to explain it as fast as possible, and of course I try to explain it. So of course generally we can see even that our pitch classes or the pitches could be could be projected in a circle, and then of course if I have this major triad, then I can draw it like this. So next line, so C, E, G. So, and of course generally if we rotate this thing, then it would be it is transposed. There is another there's another concept. Concept, of course, as we see, we know major and minor triad. They are quite similar, and they are structurally. We have here C, E flat, G. Of course, they are so-called inverted, so that we see the minor third is down, is on the lower position, and the major third on the higher position. And of course, in pitch class set theory, normally that is taken even as one and the same phenomenon. Of course, that is questionable because they are even sounding quite different. And I have found in the internet the pitch class set table modified like this, where we have every inversion extra written down, so that the version with the B is the inversion, what of course Ford recognized as the same phenomenon. And I like this conception. And if you have here asterisk, then of course it is a collection what have no what inverts it by itself, so that self-symmetric. So of course, and we have okay. Let's see another table. I have to. Here I have it. So here we have a little bit more compact table. Of course, here it is with without the inversion extra written, but here we can see that due to we have here the complement. That means if you have 3 pitches, for instance, then we have 9 left up to 12, and it makes it here in this table quite short that we have the complement there. Of course, one very important feature even for what is used for systematizing all this huge number of possibilities is the interval class vector. So generally interval class, we even interval names not after the traditional names, we have numbers for that, just a difference in half-tone steps, and then the inversions of the intervals, so that a minor second and major sevenths, major second and minor sevenths, or fourth and fifths, they are collected together and taken as one and the same thing, and this is named an interval class, because if you rotate the chord, then they are rotating too, so the conception must be that is the reason why we even need that. We cannot do it without this conception. So, and then here it is 1, 11, 2, 10, 3, 9, 4, 8, 5, 7, and 6 is identical with itself. So generally, of course, here then for classification we see what is the most compact version. So maybe I demonstrate it again on the major and minor triad. Of course, if this and this of course is the inversion, then of course we see that here we see that the E flat is more closer to the starting pitch, and of course generally if we rotate that, of course this is wider. It's also wider. We should look for the most compactest structure, and that will be the label for the so-called prime form, for the form what will be organized in our catalog of pitch collections. So, and they are then numbered, and we get here these so-called Forte names. So 3 means that we have 3 pitches, and this is the first one, and then. But the order is going after the interval class vector. Interval class vector is like this, that we count how much intervals we have inside this collection. So, and that means we count from here. This is a minor second, a major second, minor third, major third, and so on, up to the tritone, and then we mark with the number in every digit how much we have. And then we take that as a decimal number. And then we count downward. So what is the number? 210,000 is the first, and then this is smaller, 100,000, 111,000, 101,000, 100, and so on. And the descending interval class vector is the criterion by for the ordering these prime forms. So, and because of course there is of course this discussion, is the best way to order, but of course due to the fact that Forta's table is established like a standard, so that I think for microtonal pitch class tables we should exactly take the same principles for to be comparable. Of course, then comes the problem. What we will do if we have not 12 pitch classes, we have 13 or even 19 or arbitrary one, then of course it's logically that we have the cardinally three collections of three different pitches. They will be in Boland piece more, Pierce more, and even more in 19 EDO or in a 19 system, of course. And for that, I have here my proposal how to extend the nomenclatura of Fort, and I put in the beginning the modulo classifier, what system we are. Then, of course, the cardinality slash and the sequential number and additional features as in this Solomon table I showed before, this green one. If we want to specify the inversions as different phenomena, and then of course I think sometimes it's necessary that we even have to specify the rotation number, so that the classical inversion it is. We have, of course, this is one problem in Forta's table. It is not 100% of course compatible to classical music theory. If we have a dominant 7th chord, it is what was it, 426 or whatever. Then of course this is the most widest form, and the most compact form is that. But traditional that is the inversion, and the code version, the main version is like this. So, and if we want to specify that we want that, then we have to say, if we come from this, then this is 0, 1, 2. So, and then I propose that would be maybe. It's not yet the standard, only standard for myself, and the standard for myself is not the standard. So I will mark that with the rotational number as an upper script. So and here we can, as a modulo classifier, we can use these EDO numbers or just modulo. If we say we have talked about modulo 13 systems, but it could be Boland Pierce, or it could be even EDO 13 or some other scale in a framework, in a other period of depends what we want to describe. Of course, nothing to say that EDO 13 pitch class will be found completely as a Boland Pierce pitch class, but here this is my proposal how to specify pitch classes for microtonal context. So of course, but now let's go more practically. Here as Max MSP, I just in the morning programmed 3 different machines that can generate chords. I have here, just for demonstration, the major chord, this is the major chord as we know it. This is the major chord in 19 EDO. Of course, you see here the major chord is here than 0, 6, and 11 because we have more steps in the octave. The difference is quite small. If you don't carefully listen, then you don't recognize it. Here. If you listen and concentrate on the third, then you listen that the third is much cleaner. Or it's something like maybe string players will play it more like this than like this. Yeah. And now, but we can listen, of course, the steps are so unfamiliar if I transpose it. Okay, that is real what we maybe remember yesterday from the fanfare. So, of course, and here as an example, bowl and pierce. So, okay, I have here also the possibility to listen at the successive. So, but here, and then, okay, he projects it back here in this circle. And of course, I must say very much thank. I have not time to write it down in all a list out the contribution, but there is a big thank to the programmers of the Bach project of Andrea Agostini and Daniele Gysi, two Italian programmers and composers and musicians. They started just 8 years ago to make a system what is capable to have a functionality like open music, so you can compose and have a music stuff and notation system inside Max. And they also thankful that they added this pitch class set theory mathematics, and not only limited to a modulo 12 system, but it should work in an arbitrary modulo system, so that I can here in the middle is specified modulo 13, modulo 19. Of course, I very hope that there are mathematically no mistakes, otherwise I'm fooled with my theories. But of course, until now I have no reasonable mistakes discovered, with exception here something the appearance. There are, I cannot make that the numbers here appear. That's some not so important mistake, but generally the calculations, as I could recognize it, it is all correct. So, and from that I calculated this table of pitch class sects for bowl and pierce, and we can see at or modulo 13. Of course, it's that's the question: what music you want, or what system you want to describe. If you put here in front the BP or the modulo 13. Of course, BP and 13 EDO is identical. So, and here, of course, we have another thing that, of course, the intervallic inversions are different. So, because we have 13 pitches, so that means the number 1 and the number 12 is one interval class. Number 2 and number 11 is one interval class. Number 3 and number 10, because the interval class, both intervals have to give the addition for the modular number. And so here I have also specified the B version, what is the inversion. So I did that in relation to the Solomon table, and because I think that are important features for a composer to see and to figure out and see here the classes, and at the end reproduce it. And but generally, it's maybe a little bit boring. You can see here they are all existing, and okay, you cannot really check that. For that is a little bit too much information. But for that, I will give a little insight how I did it practically. So let's see, where is this? Oh, this is not that. Too much. Microtone are fourth generation. So, and of course, I had here a lot of steps, and now I think we should generate. So just a few days ago, I had the time to. First of all, the patch was only usable for modulo 13, but I had some modification, and now it should work for modulo 12 until to modulo 24. So, and here we can maybe specify the cardinality of 3, and we have the 19 EDO, for instance. So, and then first of all, I generate pitch classes in lexical order. So that looks like this. So this is 153. So all rotations are here separately. Next, filter out the rotations. Oops. So it calculates, and here we have just 51 only. And of course, here I wrote the rotations, rotation consecutively. 0, 6, 12, 0, 6, 13, 0, 7, normalized rotations. So that is, I need them later. So then, okay, order rotation after prime form. That means I look for the most compact version, because in this table I cannot be, I don't see here what is the most compact form. So 0, 6, 12, more or less, it should be the first one, but not every time. So it is not, okay, here can we see 0, 3, 15, 0, 12, 16, and here the most compact form is on the end. So that's the reason why I need even this step. So add in, so order after prime form, this computer is calculating, and here I think we should have here this 047 is here on that place. So next is number 4, add interval class vector. So calculating interval class vector, and that was the modification I made 2 days ago, because the interval class vector is divided by modulo by 2, so it means 12 and 13, and with cutting out the comma 5, the 0.5. So that means 12 and 13 modulo have 6 interval classes. 14 and 15, 7, and so on. That means our EDO 19 is 18 by 2 is should have 9 interval 9 digits in the interval class vector. And now let's calculate it. And then we see here in this table we have here the interval classes here in front, and here all the rotations. And the next is sort after interval vector in descending order. So that what Forte has done. I think in that time he did all manually. I think a year about that. I don't know. Or did he with this computer? I have no idea about that. So okay, and here we have all of them. So, and the next step is sort interval multiple pitch class after compactness. So of course, if we have like minor and major triads, so we have first inversion must be the minor. So and I do execute this, and of course I don't know why that was so complicated. The general patch I made 2014 in summer and compiled this table, but I just had some doubts, and so now I feel fresh enough and good enough to bring it to some publication in future. So and here, so this is just the old one. I calculated 4 before, so let's have here a click. So generally I could develop further that I have one click and all calculation will be automatically. So, and here we have, of course, pitch classes from 3.1 to 3.30. So that in, of course, in Fortis table there were 12, I think, I remember right, but here they are already 30. And of course, here is only text format. I am not able to add here some this subscript index. And but generally here we can format data text for the spreadsheet. So I click here and then we have it like this, and I can make copy and paste. Let's open file, new spreadsheet, and copy that here. So and here we have, then we can say we have the name, then we have the each vector, and then here we have the prime form, and then here first rotation, second and third rotation, and that's all. So with that machine I hopefully can do it. Can generate a huge number of tables, or of course as much as we have. Of course, generally I skipped, of course, the cardinalities 1, 2, and modulo minus 1, because modulo itself, that is the aggregate that have all pitches together. There is no other possibilities, and two of them, two pitch classes, they are the intervals, and of course you can say maybe it gives something the modulo minus 1, but of course it's just you pick one pitch out of that. It's not so interesting, and of course generally acoustically, if you have too much pitches at the same time, of course it is not anymore so necessary to have it all systematized, because if you have really a cluster of 11 pitches, how can say which pitch is missing? So it sounds so similar that for compositional purposes it is not so sensible. So, but generally then I have here another patch, and that's the last thing I will show. This is BP chords and scales. Of course it looks a little bit weird, but I have another view here. So, and here I have, it is a whole table. I put it differently so that I can count, so it is ordered like this, and this is the one moment, I have to see it goes to the right synthesizer that we, okay, no doubt, and it is pole and pierce, so that means we have bus 1, and of course I have, okay, let's send it to the second MIDI channel. What is our pole and pierce? Hopefully, I know, again to IAC driver to the bus. So, and again, so, and now I can here go through all pitch class sets and listen to them. Now, okay, it's generate, but I don't know why it will not sound okay. I don't know. It's computer technology. So, but of course here I can go, okay. So I made it, I have to. Of course the interface is very poor, so I cannot choose maybe a cardinality and choose like from a table. So, but of course I can. This is just order number of all, but those really says really nothing. But But of course, if you search for something, you think in the table you need 511, then you search as long as you find that. Now I have 511B, so. So, but also I can put the inversions in the starting from the same pitch, so that sounds so like. So let's listen to the Poland piece main chord. It should be 3, 14, and 3, 12, 3. So, and here we see interesting thing is that this second rotation is the most compactest, and of course it is an accident that major triad, or it's an accident in the structure, of course, that the major triad in a quartet table is appears as the root in the root position, because the dominant seventh chord isn't like this, so that is not natural that it has to be. And here we see the most basic triad. And let's listen the inversion. Okay, it sounds like this. And also for the inversion, the acoustically radiant version is not in not the first version. So, of course, if you want to listen it on a other higher pitch, okay, that is just a sketch, but in future I think I will publish these patches as tools for composers they are interested to compose in Poland here. And so that is the thing. What I think that, of course, you can have the synthesizer where you have the map, and of course it's also, before I made that, of course I learned how to play it on a traditional keyboard, and 13 pitches, the Tritthafel interval, this is of course minor ninth and so on. You can learn this different intervals, and for experimenting it is quite useful if you, unless you want not to build Poland PS keyboards with different keyboard layout. People have done it. And so, but that was my short presentation about microtonal pitch class sets, and if you have questions, then please feel free. Yeah, Giovanni.
We have talked a lot about all these things, but I've never asked you what led you into these worlds. What started all of this interest and great knowledge that you now have about the microtonality?
Curiousness, I think. I think the answer is simple, so that every time I'm like this, I look what is existing and I discover something. It focuses my interest, and I try to learn more and more. And if I see something what I maybe never seen, then I research it by myself. And I asked in Helsinki, and so nobody has yet done these type of tables.
Mm-hmm.
Maybe somebody has done it, it's not published. Every time inventions or developments then can be happen parallel.
Have you written music with this?
Yes.
Oh.
Have you time for listen music?
How long we will discuss, because I suggest to finish here 5:30. So. Yeah.
I have a question.
Yeah.
In the title, in the program, it says heliklasside hulgateooria, so it's set theory. Is it to the set theory in the sense as it a mathematical set theory? So
Yeah, there are, of course, I forgot to say, there are terminological discrepancies. first of all, a mathematical set is an unordered collection. So, but that what Ford is named set is a group in mathematics. So a group is ordered, and is a group that was cyclical or ordered. So that this belongs more to mathematical group theory. But I planned, because I'm not a mathematician, so I try to understand as much as I can, and I, of course I'm very interested to learn more, go to courses or whatever. But of course this group theory, maybe it's not so popular, not the most popular branch of mathematics. For engineers, for instance, there's more calculus and linear algebra and all these things. They are, but of course I haven't looked, and maybe there should be some courses they cover like that, and of course, and then if it's on a higher level, then there are so much basic things I have to repeat or to. And so I use the terminology of Ford, and if we say in the context of music theory, so every music theorist know what it is, and there I think these misunderstandings, it's impossible to avoid. But if we clarify it and if we make a table what Ford means and what the mathematicians say about that, then it should be clear. It's the same like in physics. Physicists say tone, and it means time tone, and tone in music is can be a whole spectrum. So, more questions? So if not, then maybe let's play the beginning of one of my piece. It was performed 2017 by Ensemble U, and it is for Poland Pierce recorder, for Poland Pierce clarinet, for synthesizer, and Poland Pierce tubular bells, what I have built by myself. So maybe we can have no time to listen it to the end, but tubular bells and synthesizer. Of 13 different keys, and it comes back, and of course I by myself don't understand where the modulation exactly going. I'm not so good trained yet, but it's very clearly understanding when we come back to the home key. maybe that underlines it much more better what are my interests in bowl and peers. So, is there still questions, or then I think we are a little bit over in time.
Thank you.